All right, let's see. Is the mic working? Is it picking me up? Let's test. Where on earth are the meeting controls? Can you hear me?
We can hear you.
Thank you. All right, so a couple of things before we get started. First, in my usual, here's a book I like. I want to tell you the story of Alan Turing, who is one of the great heroes of World War II. He was a mathematician, not a physicist, but he is arguably the reason why most people in Europe don't speak German today. Alan Turing, before World War II, was a mathematician who worked out what are the fundamental limits to what a computer can and can't do. What kinds of calculations can and can't be done if you have a machine that can perform certain kinds of logical operations. And then in World War II, he got recruited to work on code breaking. And he broke through. He wasn't the only one, but he was one of the main people on a team that broke through the encryption on Enigma, which is or was the encryption scheme that the Germans used to communicate with their submarines. Once he broke through the encryption on Enigma, then it was possible to spot German submarines, figure out what they were saying, what their orders were, where they were going, and stop the German submarines from disrupting shipping so that the U.S. could send supplies to the U.K. And the U.S. sending supplies to the U.K. is half of what enabled the defeat of Nazi Germany. The other half of what defeated Nazi Germany is that the Russians were simply willing to sacrifice even more lives than the Germans. But anyway, Alan Turing is arguably the reason why we don't speak German. And this is a really good biography of him that doesn't just talk about his World War II exploits. It also talks about what he worked out, his contributions to the history of the computer, and really one of the heroes of our world. Okay, now, the other thing I want to say before we get into today's topic is over spring break, I was talking to a cousin of mine who is about to graduate from college, and the big question is, well, what sectors of the economy are or will be hiring? Now, most of you are still at least a year or two away from graduation, but you're probably looking for internships. And I guess I would say the following. You notice how everything has gone online? Share prices for Zoom and companies like that are skyrocketing. So there will be a lot of money there. Meanwhile, anybody who makes equipment that supplies virology labs or medical labs, people will be hiring there, which means that they will be hiring on both the technical side and also the grunt work side. Now, of course, with millions going unemployed, everybody on the face of the earth right now is applying for those jobs. All I would say is that more than a few years ago now, 8 years ago, one of our best graduates was in a summer internship at a company where, for one reason or another, they stuck her in an office on the sales side rather than the technical side. And so she took that lemon and made lemonade and figured, well, I get to spend the summer on the phone with everybody who buys technology from this company. And so she spent the summer on the phone with everybody who buys technology from that company. And eventually the idiot manager who stuck her in an office rather than a lab was fired for apparently unrelated reasons, but the guy just didn't have his act together. And they promoted her to something technical. In the meantime, she had friends at every company that bought technology from this firm. And the following spring, when she was graduating, she had many, many offers to choose from. So I guess what I'm saying is that as terrible as things are, there are certain sectors that are hiring. And getting your foot in the door there by any means necessary is better than not getting your foot in the door there. So I'll say to you what I said to my cousin. Look at anybody who has a contract with public health agencies. These things are public record. You can go and search and see who currently has contracts to supply lab equipment, lab tests, all sorts of supplies for the County Department of Public Health, the State Department of Public Health, the CDC, the NIH, the Public Health Service, and so forth. Look at that. Look at look at which companies are making video conferencing software and anything related to that. Look at who's making e-textbooks. Mastering Physics, WebAssign, Wiley Plus, McGraw-Hill Connect, all of these terms for online homework systems. They have lots of people on these teams. Besides having programmers and besides having schmoozers who go and try to persuade professors to buy them, they've got content experts. They've got people who know physics or math or whatever it is that the textbook is covering. Granted, everyone else out there is going to be seeking these jobs too, but one thing you can say is, hey, I used Blackboard. Hey, I used Wiley Plus. Hey, I used Flip It Physics. Hey, I used whatever. Even if you didn't use it in a class, are you a learning assistant? Go and say, I was a learning assistant for a class that used Flip It or Wiley Plus or whatever. And even if you're applying to a company that doesn't make the product you use, just say, I took a class or I TA'd a class or was a learning assistant for a class that used online homework. I'm familiar with it. It was one of your competitors' products, but I can see the advantages of your product over the one I was using. And they'll love to hear that. Okay. With all of that stuff out of the way, let's get down to some physics. So we've been talking about diffraction of light from many different kinds of systems, from one-dimensional slits, from rectangles, from squares. Now we're going to talk about diffraction from a circle, because some of the most important things in optics are usually circular, namely lenses. And it's going to turn out that when you send light through a circular aperture, you get alternating bright and dark and bright and dark spots, but they're rotated around so you get a pattern of rings. And we're going to work out later what the angle is where how far off axis you have to go so that you go from the center bright spot to the first ring of darkness on the pattern. God, a ring of darkness sounds like something from a fantasy novel. I'm going to show you a more accurate illustration of that. This is a program called ZMax. And what ZMax does is it simulates the behavior of lenses. So we've got an object one focal length away from the lens. And then we have another object off axis, also one focal length away from the lens. And if the object is a distance y off axis, all of the rays in principle should come out on the other side going parallel to each other, making an angle theta with the axis. Here you can see that the green rays are all from the off axis object. The blue rays are from the on axis object. And whereas the blue rays go horizontal, the green rays make an angle. And if we zoom in, we see that the green rays are all pretty much parallel to each other. And they're making an angle given by y equals f tan theta, or tan theta is y over f. That's what you should have found on the assignment for today. Now, they're not quite perfect, but they do something like that. This is ideal. This is if we didn't take into account the fact that light is a wave. But of course, we know that light is a wave, and we know that the light is going to spread out. In every other case we've looked at where light goes through some finite aperture, it spreads out. And let's note that even though this lens is not a flat surface, I'm going to turn off the off-axis object. The time it takes to go from the object point to here should be the same as the time it takes to go from the object point to here, or here, or here, or anywhere else on there. All of these paths took the same amount of time to get here. We talked about that a few weeks in class. And the fact that all of these paths take the same amount of time to get from the object point to this surface of the lens means that what we have here is a surface of constant phase, which is just like every problem we've done with an aperture so far. Now, ZMax can do more than just model rays. ZMax can compute the pattern of the light spreading out. So here what we see is light intensity versus angle, either angle with the y-axis, so that on this layout, like if it's making an angle with the positive angle with the y-axis, the path would be going like that, or angle out of the screen. If we're making an angle with the, if we're going up in the y direction, we'd be making an angle with the x-axis, or it could be going out of the screen. Either way, it could either be traveling in the y direction or the x direction or some combination of the two. And so it actually spreads out a little bit like this. If we look at it heads on, you see a bright center peak, and then you probably see some faint ripples around the edges, right? This is an exact calculation for this lens shape. We can take a cross section of it, and this is light intensity versus off-axis angle. And you see a peak, and you see a node, and then another peak, and then a node, and a peak, and a node. And this is exactly what and I can make that a little bit, no, it's already pretty sharp, never mind. You can see something that looks a lot like the patterns we've seen before. It looks a lot like the diffraction pattern of a single slit in one dimension. Now, I'm not going to ask you to use this program in this class. If you want to learn how to use this program, take Physics 3440 next spring, Applied Optics. All I want to communicate to you is, one, that if you do the exact calculation of how the light actually spreads out for a system like this, then instead of getting parallel rays, you get light spread out over a narrow range of angles. And two, there's software that can do this, and we use this software in more advanced classes, and this software gets used in the private sector. Safe to say that there will still be plenty of military contractors, and there will also be plenty of people making microscopes for biology labs, and they will want people who know how to use this kind of software. Now, let's take a look at what happens if we change the wavelength of light, or if we change how wide the aperture is. Because in every other case we've done, we have found that the angle that the light spread out over depended on the wavelength of light and how big the aperture is. So what I'm going to do right now is I'm going to change the wavelength from 0.55 microns or 550 nanometers. I'm going to double that to 1.1 microns. Now let's see what happens to that first node. It takes a while to do the calculation because I asked it to go to high accuracy. Oh, okay, and we see that it widened considerably. And there is a reason why it looks like this. The lens is now slightly out of focus, so I need to refocus the lens. Don't worry about the details there. Let me just do that refocusing. Before, the peak, the first node of this was at an angle of almost 0.07 milliradians. Now it's almost at 0.14 milliradians. So one thing we can speculate is that the angle, or at least the sign of the angle, must be proportional to the wavelength. In every other case that we've done so far, we got something like that. We got something like sine theta equals lambda over aperture in virtually every other case. The other thing we could do is we could make the aperture narrower. I'm going to divide the aperture diameter in half. And we're going to see what happens to this. When I divide it in half, this first node goes from being slightly before 0.014 to slightly before 0.028. So what we can conclude is that sine theta must be proportional to the wavelength and inversely proportional to the aperture diameter. Any questions on what we've done here? And if you don't want to speak, I can also look at the chat if I can get my Zoom controls to come up to show me the chat. Any questions at all on this? It's worth noting that so far all of this looks pretty ideal. I said to you earlier in the semester that lenses stop behaving ideally when the aperture diameter gets wide. And ZMax can do those calculations too. All right, we are going to see, oh, it's still not that bad. That's mildly surprising. I thought it would be worse. When I look at the spot diagram, okay, I think I see. When I look at the spot diagram, it got spread out more, but it's not showing up in the diffraction pattern. Don't worry about that. This is technical. Let me change the wavelength back to what we were originally working at. Yeah, okay, now that's way out of focus. This that you see over here is actually quite different from what the ideal theory would predict. And the reason why this exact calculation is giving something different from what the idealized theory would predict is that this lens shape is spherical rather than the hyperbolic shape that we worked out in class a while ago. And ZMax actually allows you to visualize how non-ideal it is. It shows here the ideal case. If we just did a very simple calculation and we had a lens so good it matched up with the ideal calculation, and then it shows us how the energy is actually spread out. It shows us that if we go out 1.1 milliradians away, we only have 30% of the energy enclosed, whereas the ideal case would suggest 95%. Again, we'll interpret all of these in a more advanced class. What I want you to take away is that there's software that can find out what's actually going on in a real lens with real imperfections. Okay, so back to this. Hopefully you can see that the idealized case sketched out in my notes and also sketched out in the textbook matches what a more accurate industry grade calculation gives you. We can get a qualitative understanding of that if we look at, say, a path from the top of the lens to a distant detector and a path from the bottom of the lens to a distant detector. And they're making an angle theta with the axis. And then the path difference, this angle was theta, so this angle will be theta. The lens diameter is the hypotenuse of a right triangle. The path difference is opposite theta. And that difference in path length is a sine theta. And if these were the only two paths we had to worry about, then we would get destructive interference, or that little dark ring, that first node that we were looking at in the ZMax calculation, when a sine theta is lambda over 2. Of course, these aren't the only points on the lens. These aren't the only paths that light could take from the lens to the detector. Most pairs of points on this lens are actually closer to each other than these 2 points are. So if I were to just pick some arbitrary point here and some arbitrary point there, the path difference there would be some distance multiplied by sine theta, and that distance would be less than a sine theta. All right? So we're going to have a whole bunch of paths that differ from each other by less than a sine theta. So if the largest difference were lambda over 2, all the others would be less than lambda over 2, and we're not going to get destructive interference. What we need is for the average path difference to be lambda over 2. And it turns out if you do a more elaborate integral, an integral that I'm only going to sketch out the beginning ideas of, because it involves things you'll get in more advanced classes later, you would get that this average path difference is lambda over 2 when the maximum path difference is 1.2 lambda. Goes like this. Here's how we get that. Let's look at, we're going to compute everything relative to a reference path from the center. Now let's say we've got a point somewhere here in the lens. It's not along the central line, it's off center. Well, the first thing we could do is go out along the x-axis and draw a path that's parallel to this. Now this path, which has been displaced along the x-axis, displaced perpendicular to the main path, actually takes the same amount of time because the displacement between these two paths, it's not entirely obvious from the way I've drawn it, but try to imagine a displacement into the page. That's not changing the path length. Then we ask, what's the difference between this path here and this path? And this path got displaced vertically. Now, vertical displacements do change the path length. So we got a hypotenuse y, we got an angle theta here again. This difference will be y sine theta. So our path difference is y sine theta. And we have to add up e to the iky sine theta everywhere here because all of those phase shifts from the waves will be e to the ik path difference. All right, now instead of writing y sine theta, I'm going to write y in terms of coordinates, in terms of polar coordinates, because we're integrating around a circle. When you integrate in a circle, it's much easier to work in polar coordinates. Your limits of integration are that your angle goes from 0 to 2 pi, and your distance from the center goes from 0 to the radius. If you tried to work in Cartesian coordinates, your limits of integration would be much, much messier. So y is r sine phi. We got e to the iky, or e to the ik r sine phi sine theta. And then this is the differential element of area in polar coordinates. And we can't do this integral in terms of anything you've learned thus far. All right, it involves some functions that you're going to learn about next fall in math methods, and they're called Bessel Functions. And I'm just going to assert that if you do all the math, you come up with this messy expression. 2 times j1 of ka over 2 sine theta. j1 is a Bessel function. And I'll show you the graph of it in Mathematica. It's going to have a 0 right there. So let's go into Mathematica. I posted this Mathematica file on Blackboard. This weird Bessel function, or Bessel function divided by something multiplied by 2 and squared, it has a name. It's called the Airy function, or the Airy point spread function. Point spread function is a technical term in optics. And if I play with it, we've got an Airy function with input ka over 2 sine theta. And I can plot it, if I plotted it from 0 to 90 degrees, you can barely see it. And if I make the aperture width anything appreciably different from the wavelength of light, then you basically don't see anything because the graph is so narrow. You have to have, well, why don't you take away is this angular spreading is usually pretty small, okay? And the reason it's important that that angular spreading is usually pretty small is that's why it took people so long to discover the wave nature of light, a theme that keeps on coming up again and again. In all of these situations, the angular spread of the light is very small unless the aperture size is very, very tiny. Because I can assure you that if this were even close to being easy to work out, the Greeks and the Arabs would have worked it out 1,000 or more years ago. If not the Greeks, then certainly the Arabs. And then they would have discovered the existence of emission lines from atoms, which means they would have discovered atoms because they would have had to make sense of all this emission spectra. Then they would have discovered the nucleus. Then they would have had a nuclear war, and we would be living in radioactive ruins. You may be thinking, well, why am I assuming that they would have a nuclear war, but we won't? Who says we won't? It might take a few centuries. Anyway, so this function is going to be very hard to work with because Bessel functions are weird things that people don't have a lot of experience with. So it's worth noting that they usually approximate it with something called a Gaussian, which just sounds like another word, but a Gaussian is basically e to the minus a constant times all of this squared. This Ka over 2, keep forgetting the 0.5, Ka over 2 sine theta. Instead of taking Ka over 2 sine theta and plugging it in to that Bessel function, what you could do is take K over 2 sine theta, square it, multiply it by a constant, and then put that in an exponential. And that is something that you can at least write down easily on paper. And it turns out that if you pick that constant in the exponent just right, then the two functions look pretty similar to each other. That Gaussian looks, it's never exactly the same as that Bessel function, but it's close. And in most real calculations, people will work with a Gaussian. Now, again, I don't expect you to take away any details of Bessel functions. You could think of some of this as just, here's where it all comes from. Here's a preview of what you're going to see in the future. If you take nothing else away, take away that right now some of this stuff is too complicated to explain with the mathematical tools that you currently have. So I wind up just making assertions. Oh, it's this thing called the Bessel function. Oh, the Bessel function is 0 when the input is 3.83. This is you probably find that unsatisfactory. That's why you should pay attention in math methods next fall, because next fall we're going to do things that you won't have to take for granted. Let me show you one other thing. I might as well just, while I'm at it, show you where that 0 is. So let's plot the area PSF versus x will just be its input, x from -6 to 6. Okay? And it looks like this. It looks a lot like that sinc function we worked with. The details are a little different, but it's got the same basic shape. Let's just verify where that 0 is. I asserted that it's 0 when its input is 3.83. Right now, it looks like the 0 is somewhere between 3.5 and 4. Let's verify that. Somewhere between 3.8 and 3.9. Looks very close to 3.83. We could verify that even more by doing this. Yeah, it's actually 3.83 something. All right, I've thrown a lot at you so far. Before I go on to the next thing, I want to pause for questions. Either speak up or type something into the chat. Anyone? Going once. Going twice.
So, Professor, for the Bessel function, the zero is always at 3.83.
For this kind of Bessel function, it turns out that there are many kinds of Bessel functions. For this kind of Bessel function, it has a zero at 3.83. That's not its only zero. If we were to zoom back out, we see that there's another zero at 6 point something. And if we were to zoom back out again, we would see that there are additional zeros. And we need to be careful. It's whatever number you plug into the Bessel function that's equal to 3.83 when we are at that first zero. So Ka over 2 sine theta, that whole thing is equal to 3.83. It's not that K is 3.83 or theta is 3.83 or A over 2 or whatever. It's the entire combination together that's 3.83. Other questions? All right, so let's make use of these facts. So the field is 0 when K over 2 sine theta is 3.83. So we'll use the fact that K is 2 pi over lambda. So we multiply 2 pi over lambda by A over 2 by sine theta. We get that sine theta is lambda over A times 3.83 over 3.14 pi. And we get about 1.22. All right, so what does this mean? This means that we can figure out how much light spreads out when it goes through a circular aperture. So let's start with something simple like a laser beam, right? A laser pointer. And in class, whenever I've done demos with lasers, those laser beams spread out very little. But of course, we know that if there is a surface of uniform phase here, if the phase of the field is the same everywhere across this aperture, then it will spread out over an angle whose sine is 1.22 lambda over the aperture. Now, the diameters of laser beams vary wildly, but let's start with something small. And let's ask, how far would it have to travel before its width doubled? Okay, because you can think of it as starting off with a diameter d. The top edge is spreading upward, the bottom edge is spreading downward. So the width is going to double to 2d if the top edge has gone up by d over 2, and the bottom edge has gone down by d over 2. So we would get that we've gone a distance L, and the tan theta is d over 2 divided by L. And here we're going to use the fact that tan theta is roughly equal to sine theta for small numbers. I'm going to push on that in Mathematica in a moment. So we could say that sine theta is d over 2L. And that's 1.2 lambda over d. So d squared is going to be 1.2 times 2 times the wavelength times L, or L is d squared over 2.4 lambda. And if we assume a millimeter beam, then we get 0.8 meters. We get that it would travel 0.8 meters before doubling. Now, let me ask you this. I'm going to toss this out to the room. You can either turn on your microphone or go into the chat and type it if you're too shy to speak. What if the beam diameter was not a millimeter, but a centimeter? How far could we go before it doubled? the initial beam diameter, I should say. It starts off a centimeter thick, and it starts off a centimeter across, and then it travels some distance L. Anyone? Well, L is proportional to d squared. So if I multiply d by 10, I multiply d squared by 100. So if the beam diameter is a centimeter, then we go 800 meters, almost a kilometer, before we see anything. We go roughly half a mile before we see any significant spread of the beam. And of course, the ancients, the Arabs, when they were playing around with optics, or Greeks like Archimedes before the Arabs, they could not usually reliably make perfectly smooth millimeter holes. If they had done that, if they could have made perfectly millimeter holes with perfectly smooth edges, so there's no roughness to complicate the beam shape, I think that with very reproducible millimeter apertures, they would have discovered this. But they didn't have that. And that is the only reason why Ibn al-Haytham is not the father of wave optics. I'm pretty sure that with reproducible millimeter apertures, Ibn al-Haytham would have figured this out. All right, now, wait, okay. Let's talk about that small angle approximation. I've been saying that sine theta is roughly theta when the angle is small. So let's go into Mathematica, and I'm gonna work right here below this graph. I'm gonna create all right, now sine theta is roughly tan theta if theta is small, but theta has to be measured in radians. So let's just play with this a little bit. Let's say that theta is 0.1. Now let's just look at the values of sine theta and tan theta. All right, if theta is 0.1, then sine theta is 0.998, and tan theta is 0.100. So these are differing by 2 out of 1,000, or 0.2%. Let's say that theta is 0.5. Okay, well, now they're substantially different, and we got roughly 0.48 versus 0.55, but still about 14% difference. It's not the end of the world. 0.2, all right, now we've got a difference of about 0.004 out of 0.2. And so now we're talking about maybe a 2% difference. Is that right? Oh, yeah, about 2% difference. So up to an angle of about 0.2 radians, these two are very good approximations for each other. Sine theta and tan theta are very similar. Once you're beyond 0.2 radians, if I go up to say 0.3, 0.296, 0.309, let's take the ratio. Right, the ratio is 0.955. which means that ratio differs from 1 by about 4.5%. If the angle is 0.2, that ratio differs from 1 by 2%. If it's 0.15, that ratio differs from 1 by about 1.2%. Now, if we say that somewhere around 0.15 or 0.2 radians is the cutoff, what is that in degrees? Let's find out. We multiply by 180 over pi, and we get about 8.6 degrees. So anything up to about 8 degrees, you can approximate sine theta with tan theta. Beyond that, you can't make those approximations. Any questions? Anyone? Let's do another example. Say that somebody gets the bright idea to write on the moon with a laser beam. They want to do a light show that will be visible on the moon. But if I shine a laser on the moon, it's not going to be noticeable to the human eye unless it's as bright as sunlight, which is about 1.3 times 10 to the third watts per meter squared. I'm saying 1,300 watts per meter squared on the moon. Why is the brightness of sunlight only 1,000 watts per meter squared on Earth? Take a deep breath and think about it. That admonition to take a deep breath is a hint. The atmosphere is the reason why sunlight is not as bright on the, why is the chat box? I can see the chat box sort of. Okay. Yeah. That admonition to take a deep breath is the hint. The atmosphere is what makes sunlight dimmer on the surface of the Earth than on the surface of the moon. All right. So let's say that somebody is going to focus this light with a really wide mirror. Okay, because we know that we will focus the light to a narrow spot if we have a wide mirror. We know that sine theta is small when the aperture diameter is big. And we know that we'll get higher intensity if we have the energy focused to a really small area. So somebody says, hey, let's work with a meter. That would be a good telescope. All right, well, the radius of the spot on the moon we'll call little r. We'll call big R the distance to the moon, and tan theta will be little r over big R. It'll be roughly sine theta, or 1.2 lambda over A. So little r, we'll just multiply by big R. We're going to get 228 meters. And we want power over pi r squared to be greater than the solar intensity. So we want the power to be greater than, if we plug in all the numbers, solar intensity multiplied by pi r squared, plug in all of that, 680 megawatts. Now let's put 680 megawatts in context. MGM Resorts is apparently building a 100 megawatt power plant for their Vegas hotels. All right? And we're saying that the power needed here is 7 times that. And you figure that the MGM hotels are a portion of the Vegas Strip, but of course, not all of the energy in that hotel is going to light up the exterior. Just, you know, if you took all the energy in their hotel and only put it on the exterior, that would probably be comparable to the Vegas Strip. So if you took all the energy needed to power the Vegas Strip, then you could produce a spot on the surface of the moon that was brighter than the sun. It would just be a little spot. It would be really small. It would be at the limits of visible resolution. So good luck in seeing that. One occasionally hears of vaporware proposals to do this, to, I don't know, generate ad revenue by, you know, projecting someone's corporate logo onto the moon. I don't think anybody is willing to pay the MGM Resorts Vegas electric bill just so they can see a corporate logo on the moon. All right, now let's talk a little more about what the eye can see, because the eye is a lens that takes all of this incoming light and focuses it to a spot. And so instead of the light spreading out across a range of angles, they try to focus it to a spot. And at the center of that spot, all these paths take the same amount of time, so they interfere constructively. We can figure out how big the spot is by asking, well, how far off axis could we go before we get destructive interference? So we're going to look at this path, the path from the top of the lens to the center of the spot, and then a path from the top of the lens to off-center by distance y, Well, that path difference is y sine theta, right? So this path here differed from this path by y sine theta. It was shorter by y sine theta. And if I look at the same off-axis point, I say how much time would it take to get there, or how much extra distance would you cover coming from the bottom of the lens? Well, that would be, again, y sine theta, but it would be ahead by y sine theta instead of behind. So this difference is 2y sine theta. And again, this is the maximum path difference. Now, the maximum path difference would be 2y sine theta. We want that average path difference to be 1.2 lambda, so that we want the maximum path, we want the average path difference to be lambda over 2. And if the average path difference is lambda over 2, that means that the maximum path difference, when adding up all of the paths coming from a circle, is 1.2 lambda. So 2y sine theta should be 1.2 lambda, or y should be 0.6 lambda over sine theta. Now let's verify that in ZMax. I'm going to go into a file now for a well-designed lens that instead of a well-designed lens that instead of taking light from a focal point and sending it to infinity does the opposite. I was asserting in these notes that we get a pattern like this. A pattern like that is also drawn in the textbook, but I always like to go into the ZMax simulation and actually see it happen. So here is a well-designed series of lenses, and you're wondering why on earth would anybody use that many lenses? Basically because all of the imperfections of the lenses cancel out. I don't expect it to be at all obvious to you that all of the imperfections of these lenses cancel out. It took a very large team of people to design these lenses. They got a patent for it. They got paid very well by their employer for doing that. But it does indeed turn out that you take these parallel rays, they get spread, then recombined, then recombine some more, then spread a little bit differently, then recombine several times, so that all of those imperfections cancel out. In the end, they all come together here, and if we look at a cross-section, indeed, we get something like this. We get a shape where now this is intensity versus distance from the center of focus. And I cannot design a lens like this, but I can use the software that takes someone else's design and simulates the performance, and I will teach you how to use that software if you take applied optics next fall. All right, so spot size is 0.6 lambda over sine theta. And this angle, it's important to see that this angle here is not the angle that light spread out over when it went to infinity. It's rather the collection angle. If I go back into this design and just zoom in here, you see how there's two sets of rays. Let me get rid of one of them. You see how the light came in here and here, all right? Comes in over a range. It's the range of angles from which the light got focused. Now, if I were to make the aperture narrower, if I were to constrict the range of rays that come in, the second peak was at 0.72 microns. Now it's at 1.4 microns. All right, so when I change the range of angles that light comes in at, I change how well the light gets focused. It gets focused to a larger spot size when I collect light from a smaller range of angles, or focus light from a smaller range of angles. And what I basically did, if I play with this, is that I decide, hey, instead of sending in a wide beam of light like this, I'm going to send in a narrow beam of light like that. And when I send in the narrow beam of light, then over here, the light is only coming in at a small range of angles, so it gets focused to a larger spot where the second peak is at 1.44 microns. Where if I send in light over a wide range of angles, it gets focused to a narrower spot where that second peak will be in a moment at 0.72 microns. Again, the details of ZMax I don't want you to memorize. That's a whole other class. What I want you to take away is that light spreads out over a range of angles given by sine theta equals 1.2 lambda over A. If I have parallel rays of light and I send them through a lens, if I have parallel rays of light coming out of a lens, they spread out over, they don't remain parallel. We set up the lens to try to make them parallel, but instead they spread out a little bit over an angle given by 1.22 lambda over A. And if I try to focus them with the lens instead of collimating them, instead of spreading over a range of angles, they spread out over a range of distances rather than going to one point. That range of distances is 0.6 lambda over sine theta, where this theta is the collection angle of the lens. And sine theta has a technical name. It's called the numerical aperture. Next time what we're going to do, we're going to continue from these same notes, and we're going to work out what that means for imaging with the lens. How close together do two objects have to be so that their images, how far apart do two objects have to be so that their images can still be resolved? And we'll apply that to some situations with both microscopes and telescopes and the human eye. And then I will show you the frontiers of optics research. Any questions? Anyone? Anyone? Going once? Going twice? Okay, then, that's all for today. I will pick up with this on Wednesday, and as always, I'm available to take questions during office hours. Send me an email. We can do a Zoom chat or a phone call or whatever. Have a good day. Bye.